All right, everybody's done, pretty much. Homework is due. You can leave it for me up front here. I had a question about driving force for skeleton redox. Yeah, you should show me what the driving force is. And so, showing me what the driving force is, you just have to identify what the oxidizer is, what the reducer is. And we already know there is a driving force because a skeleton redox forms products. The products that are given in a skeleton redox are the major products that were observed. And so we just got to assign. Now, assigning what the oxidizers and reducers are, the easiest way to do that is looking at the balanced half reactions, right? And so from that, you should be able to get it. If you have a specific example, we could take a look at it. But are there any other questions about reactions or anything like that? No. All right, let me finish this, what we're talking about regarding chapter 15. And so we looked at experiment 1, and we saw it looks like there was 36% reaction for copper 2 and 68% reaction for tin 2. Did we look at experiment 2 yet? Yes, we did. We look at experiment 2, and we expect to see some kind of ratio like that here, but do we see the same ratio? No. Okay, then let's go to experiment 3, because, you know, what's the scientific method? What do most scientists do? How do they do their work? Well, you know, in science, we take observations like this. Observations are experiments. You know, once a student was telling me observations are not an experiment. Observations is a visual observation. No, observations for us are just taking down numbers and this kind of stuff. These are measurements, in other words. And so we look at, we take observations like this, and then what do? We try to find a pattern, right? And so have we found that pattern yet? Have we found? No, we haven't found that pattern yet. And so let's try to take some more observations and see if the pattern appears, right? And so the next experiment, which is copper 2 plus tin 2, need 2 of those, is going to yield 2 copper 1s plus a tin 4. And we set up our ice table like this. And so initially, now what we're going to do is we're going to put 100 moles, 0.100 moles of each in here. Just so we can see if some kind of pattern emerges in how we should treat these stoichiometrically. And so, do we have to measure all the equilibrium amounts? No, all we need to do is measure one. If we measure one of these, let's say we just measure the copper 2, the copper 2 equilibrium amount comes out to 0.0922. Oh, this is 3 sig figs. And so the reason why we only need 1 is because of the reaction ratios. You know, for example, copper 2, how much of it reacted? So if we start off with 100, we end up with, yeah, it looks like 92.2% remains. That means I must have lost 0.0078 moles. In other words, I must have lost 7.8. So I only had 7.8% reaction. Do you see the numbers here? So if we call that 100, then I got 7.8. Right? And I'm left over with 92.2. Why only 7.8% this time? You know, the first time we did it, we got 36% reaction. This time we only get 7.8%. Do you see a pattern? All right, all we need to do is measure one of these because we could figure out the others. And so if 0.0078 moles of copper 2 reacted, how many moles of tin must have reacted?
92.2.
All right, so this many moles of tin must have reacted. 0.0, 0. In other words, when I'm asking that, how much tin reacted? Half this. How do I know half this amount reacted? Because twice as much copper reacts than tin. They're going to have to react in this ratio. And so if I reacted this much copper, then the amount of tin must have been 0.0039 moles. Okay, so I only lost 3.9% of my tin. If I lose only 3.9% of my tin, I'm going to be left with 0.0961. Do you see? That's what we would have measured, 0.0961, because atoms are neither created nor destroyed. So, we didn't have to measure all 4 of these. We just needed one. And then, the thing we could do stoichiometrically is this easily, because this reacts in a 2-to-1 ratio. The thing we can't do easily stoichiometrically is predict what the percent reaction is. Because in the first reaction, the percent reaction was 36. In this reaction, it's like 8% reaction, right? In the middle reaction, then we had some kind of reverse, where we had 56% reaction with the copper. And so what we're looking for is some kind of pattern that we can use. Well, how much copper plus are we going to form? Well, we could see here, atoms are neither created nor destroyed. So if I lost this many moles of copper on the left side, I better have them on the right side. So this is going to be 0.0078 moles. And so this is going to give me 1078. But sig figs, I need to, I do this for sig figs. How many sig figs am I allowed? If I add 0.100 to 0.0078, how many sig figs am I allowed? Well, am I allowed, I'll tell you, when we're doing addition or subtraction, I shouldn't pay attention to sig figs. I should pay attention to decimal places. How many decimal places am I allowed? 3. And so if I have 3 decimal places here, I don't want to do rounding, because you're only allowed 1 rounding step. That rounding step is at the very end of the calculation. If you do intermediate rounding steps in Chem 1B, you're going to get yourself in trouble. The way you're going to get yourself in trouble is oftentimes we double check our answer. When we double check our answer, let's say it comes off 5%. Is it 5% because you're overzealously rounding every number, or is it 5% because you made some kind of error? And so to minimize the, because rounding can easily give you a 5% error. So to try to minimize the error introduced by rounding, we carry extra digits. We carry extra digits, that way we don't have to worry. If there's a 5% error, it's probably something in your calculations. And so when we carry extra digits, we subscript those extra digits, so that we don't treat those as significant, but we treat those here to minimize round-off error. And so this is going to be plus 0.0039 moles, and so this is going to give us 0.1039 moles. Here. You could underline it too, whatever. You just have to keep it separate. All right, so is there a pattern in percent reaction? Can we say that the percent reaction for copper, this redox, is always the same? No, the percent reaction depends on your starting initial conditions, right? So we start to look for patterns. In science, scientists love to graph things. And so if we graph things, this is what we'll do. Did I talk about this one already? Yeah. Right? Yeah. And so what you're going to do is you're going to look for a pattern in the red, green, blue, and black. And so take a look, because the red, green, and blue, and black, this is the product mix here. And so do you see a pattern in the red, green, blue, and black that's reproducible? Do you see that? a pattern? Or does it look random? I mean, can you predict the next reaction? How the red, green, blue, and black? No. It looks random, doesn't it? It doesn't look like there's an observable pattern there. But sometimes observable patterns are very difficult to find. When you looked at the hydrogen atom spectrum, the hydrogen atom spectrum had a red, green, blue, and violet line. Those 4 lines. Did you see a pattern in those lines when you looked at it? Maybe when you looked at it, there wasn't a pattern. But there was. There actually is a pattern in those lines. You know, the pattern in the lines is given by this mathematical equation. And so those lines in the visible hydrogen spectrum fit this equation here, where n is an integer greater than 1. Right? In this case. And so maybe there's some kind of mathematical pattern hidden here that's just not readily apparent, you know? And so what scientists do is they try to fit the data to some mathematical function. You know? This is all part of the data reduction process. And so let's try to fit the data to mathematical function. Well, what mathematical function should we use? Well, we just take guesses, you know? And so a whole bunch of different guesses about what mathematical function might be applicable. And so this is one of the guesses here. One of the guesses says maybe there's a pattern in the ratio. We'll take the ratio of the products over the reactants here. But you know what these square brackets mean? The square brackets mean molar concentration usually. And so, you know, we skipped a whole bunch of steps because we don't have molar. Do we have molar concentration here? No, we have moles here. And so what we want to do is, why do we want to find a pattern? The reason we want to find a pattern is so that we can try to make some kind of prediction. And like, for example, if I go on to experiment 4 here, you know, and there's some kind of pattern to the reactivity. Let's go to experiment 4 here. You know what I'm going to do in experiment 4? Although it's not in the book, I'm going to double this. So let's start off with 0.200 moles and 0.100 moles. When I double it like that, is there a limiting reagent? No, if there's no limiting reagent, we call this stoichiometric quantities, right? This is a stoichiometric reaction. And so it should react nicely. I need twice as much copper. Oh, I got twice as much copper, right? If this were Chem 1A, this would be so easy because it ends at 0, 0, 0.2, and 0.1. But this is not Chem 1A. This is partial reaction. And so it's not 100% reaction. If it was 100% reaction, it's so easy. It's like a Chem 1A stoichiometry, but actually we don't even know what the percent reaction is, do we? There's a percent reaction change each time. So do you expect the percent reaction here to be 36% like earlier? No, we probably wouldn't guess 36%. It's probably going to be something different. And so we're looking for a pattern. And so let me make a long story short. They looked for a pattern in the moles. They didn't find it. Actually, they would have found it here, but in other cases, there was no pattern in the moles. And then they switched to molarity, and they looked for a pattern. And so what they did was they took a pattern, mathematical, try to fit the data to this mathematical function. And so when they plug in the data for the equilibrium concentrations, not the equilibrium amounts, they see this. Do you see some kind of consistent pattern here? No, because each one gives a different number. And so it's kind of random. Can we predict what number 4, that number is going to be? Is it going to be 1.0? Is it going to be 2.3? What is it going to be? We can't predict that, right? And so we're looking for something reproducible, a pattern that we can predict. All right, well, there's twice as much copper in this reaction. So what if we double the copper concentrations? If we double the copper concentrations, do you see a pattern emerge here? You know, a reproducible pattern. No. But what if we square the concentrations? If we square the concentrations, do you see something happen here? All three experiments give us roughly 148, the same ratio. All right, now this is part of the scientific method. The scientific method is this. We take observations, we look for a pattern, and then we come up with a equation. What else you guys got? The scientific method is we take our observations, we look for a pattern. So we found a pattern. What's the next step? A law. The law is a pattern that's a consistent pattern that doesn't have exceptions, right? You don't want a whole bunch of exceptions to your law. But is a law a theory? You know what a theory is deep understanding, right? And so this brings up this point, and the point is, what the heck is molar squared? Have you ever heard, if somebody asks you, hey, can you make me a 3 molar squared sodium chloride solution? And you'd say, you're out of your mind, right? There's no such thing as molar squared. And not only is there no such thing as molar squared, there's no such thing as molar cubed, right? And so why are we squaring it? Have you ever squared molarity? You know, hey, I want a super concentrated cube sodium chloride, 1 molar cube solution. That's ridiculous, right? And so the thing about these is we don't think about it. We don't think what it means because we're just at the law phase. The law phase is this. What laws are they're just mathematical equations that fit our experimental data. In science, those are called empirical equations. Empirical equation. For the one empirical equation you guys used a lot is the ideal gas law. Did you care? I mean, why is it P times V? Why isn't it P divided by V? Did you care about that? Did you ever question why is it P times V and not P divided by V? In fact, what is P times V? Do you even know what P times V is? Liters atmosphere? What is a liter atmosphere? Well, liter atmosphere is a joule, right? Or joules, energy, P times V. But did you ever question those types of things? No, you just used it, right? You just used the ideal gas law, correct? Well, let me bring you up to speed here. We found something that works. And so what we're going to do is we're going to make sure it works in a lot of different reactions, and it does. Once it works in a lot of different reactions and we didn't find any exceptions, then we call it a law. And so this would be the law of equilibrium. Although the book doesn't call it, that's exactly what it is. And so let me write down the law of equilibrium. The law of equilibrium is this. This is a consistent pattern we see over and over. And if we take any reaction, coefficient A and the reactant A, little a plus A, little b plus B plus dot, 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 however many reactants we have goes to products. Products will start with G, little gg plus HH plus dot, dot, dot. The law of equilibrium says this. The law of equilibrium says if we take the concentration of G raised to little g power, the concentration of H raised to little h dot, 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 then divide it by A to the little a, B to the little b, dot, 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 we get a constant. And so there's a consistent pattern here. This constant we give a name to, since we call it the equilibrium constant, Kc. This C stands for the concentrations. Don't need this anymore. I don't need this anymore. Well, that's fine if we have aqueous solutions, but we don't always have aqueous solutions. What else do we have? We have gases, right? For gases, you could use molar concentration, or you could use this. This is another pattern that's observed. The other pattern that's observed is the pressure of G raised to little g, the pressure of H raised to little h, dot, 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 divided by the pressure of A raised to little a, pressure of B raised to little b, dot, 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 is equal to a constant as well. And this constant we call K sub P. We know that pressure and concentration for gases are directly related. Actually, leave that up for right now. How are they related? Well, let me write that here. You know, from the ideal gas law, the pressure is equal to nRT over V. N over V is moles over liters. What's moles over liter? The concentration. And so the pressure is equal to the concentration times RT. And so what we can do is we can connect Kc and Kp mathematically. That is, we'll just connect it like this. Kp is equal to Kc times RT raised to what we call delta N of the gas. These are all just patterns that we see, mathematical patterns. And so you might get hung up thinking, you know, why? Why is it like this? You know, but we aren't. We're just going to use it like we use the ideal gas law. So the first 4 chapters are learning how to use this equation to make predictions and that sort. And then we're going to have a chapter talking about the theory. You know, where does this ideal, not ideal, where does this equilibrium law come from, right? But we aren't going to worry about where it comes from. It just works. Or we should be so happy we found some pattern. If we couldn't find some pattern, then we could not make any predictions, right? And so let's see how we can make a prediction here with this. You know, first we got to figure out what the constant is. To figure out what the constant is, we just measure the equilibrium concentration. And then we plug it in. We plug in the numbers here, and we get, for this reaction, we get something called Kc is equal to 1.48. You know, it's 1.48 plus 1.48 plus 1.49. This is going to average to 1.48. And so we'll take the average, the constants. And so we have the value. Now with this value, what can we do with this? Well, you know, this value should tell us the ratio of the product. So the product here is going to be copper plus, and the coefficient is squared. So this is going to be squared times tin 4 plus to the first divided by copper 2 plus squared divided by tin 2 plus. And so this ratio should be the N ratio here. Do you know the percent reaction? Can you tell me what the percent reaction is? Is it going to be 50% reaction, 36% reaction, 9.4%? How much percent reaction? We don't know, right? Does anybody know the percent reaction here? It's not going to be 100. And so since we don't know what the percent reaction is, we just say minus 2x. The reason we say minus 2x is because of the coefficient here. We need twice as much versus tin. So tin we'll just call minus x. But there's a problem. I already ran into one problem. What is that problem I ran into? The problem is the pattern works for molarity. Does it work for moles? No, unfortunately, sometimes it does work for moles, but the pattern's for molarity, not moles. So should I convert it into molarity at the end, or should I convert it at the beginning? Well, Petrucci sometimes converts it at the end. Sometimes it's easier to convert it at the end, but most of the time it's easier to convert it at the beginning, so we're only going to convert it to the beginning. And so I can't use this like this. Instead, what I have to do is I have to change it from moles to molarity. And so what we're going to do is we're going to have a volume. I'm going to make this easy. Let's call the volume 1.00 liters. And so if I take the moles divided by the liters, and I get molarity, right? And so I have 1.00 liters. That means this is going to be 0.200 molar, not moles. This is going to be 0.100 molar. This is going to be 0 molar and 0 molar. Okay, now I'm going to use my generic percent reaction or generic change. the generic change is going to be minus 2x. Minus x, these are both molar. So if I lose 2x coppers, I better gain 2x coppers over here, right? And so this has got to be plus 2x molar, and the tin is going to be plus x. And so this stoichiometry works here because I can't create or destroy atoms. And so at the end of this, I need to figure out what x is. How can I figure out what x is? That up there. And so what I'm going to do is I'm going to call this 0.200 minus 2x molar. This is going to be the equilibrium concentration of my copper tube. Here. This next term is going to be 0.100 minus x molar. This is the equilibrium concentration of tin 2. This is going to be 0 plus 2x, which is we'll just call 2x molar. This is the equilibrium concentration of the copper 1. And this should just be x molar, which is going to be the equilibrium concentration of tin 4. So what I'm going to do here is I'm going to substitute these into this equation here. When I do that, okay, I'll look for the copper 1 concentration at equilibrium. Copper 1 concentration is 0.100 minus x. And then it's squared, so I have to square the whole thing.